Hello everyone and welcome back. This is Mr. Keeney and today we're going over section 2.4 notes in geometry. Today we're going to be talking about postulates and then also diagrams. So looking at our I can statements and what we're working on today, again those postulates that involve points, lines, and planes, building on those foundations of geometry as always. And then interpreting geometric diagrams, identifying what can and what cannot be assumed, and actually I might underline this here. And as we go forward in geometry, working towards proofs and reasoning and logic, kind of what we're in right now, really, making sure we know what can we assume when looking at a diagram and what can we not assume. And so when we get to these assumptions, if we look here at our first bullet point, rules that are accepted without proof, meaning these are assumed to be true, are called postulates. So if there's ever something that is called a postulate, whatever, or a title of something, then postulate, those are rules in geometry that are accepted without proof. We just get to assume they are true, and you will see a lot of examples here in a second. Another word you'll see for postulates is axiom. You'll hear that. It really means the same thing. It sets up our basis and our model for geometry. If you were to continue your study of geometry into more of a college geometry setting, you might hear axiom more, and it talks about, and I've seen that used in more different models of geometry rather than just Euclidean geometry, which is high school geometry. And then, of course, we do have rules that are proved, and those are called theorems. And theorems are things, again, that you're familiar with. There's famous theorems, the Pythagorean theorem, and those come with justification. Those are things that we take our postulates, we take our definitions, we take those facts, and we're able to use those to form an argument, to form a proof, to prove them true. So theorems are proved, postulates are assumed to be true. So here are some examples of postulates, because a lot of times I get questions of, okay, I understand exactly, or not exactly, but I understand what a postulate is. Can you give me an example, though, of what this would look like in geometric settings? So here's some examples. Postulate 5, and I don't want you to worry too bad about which postulate is in this book. It's more just knowing the postulate itself. Through any 2 points, there exists exactly one line. So this is something that we just assume to be true. If I were to have 2 points, which I guess I'll sketch this one. I don't think I'm going to sketch all of them, but if I were to sketch a line through these 2 points, I would be under the understanding that this is the only line that exists. There's not more than one line through those points, and there is one. There's not zero, there's one through those 2 points. So that is an assumption. We do not have to prove that to be true. Another one is kind of almost like a converse of this. A line contains at least 2 points. We know that any line has at least 2 points. It is determined by 2 points because of what we just talked about. If I were to put 2 points anywhere in space, I would be able to draw one line through them. Next postulate says if 2 lines intersect, then their intersection is exactly 1 point, which is, again, just an assumption. A lot of these will feel like kind of no-brainers, and that's kind of the point of having postulates. They're things that we're like, well, yeah, of course. But now we have a word for that, which is they are postulates. They're things that we assume to be true. This one, we have 2 lines. They will intersect at one singular point, in this case that I sketched here at this point here. Next postulate says, through any 3 non-collinear points, and let me pause for a second. Non-collinear would mean I have 3 points like this. They're not in a straight line. If I have 3 points that are not in one straight line, then there exists exactly one plane, because when I have this 3 points here, it makes a 2D area. You guys can kind of see this here. It's making this 2D area, and so that 2D area we can extend in all directions, and so that is where the 3 non-collinear points will actually make up an entire plane. So I like to think of that in terms of polygons. I need 3 vertices to make that 2D area, and that area with planes can be extended forever. So through any 3 non-collinear points, there exists exactly one plane. Not more, not less. Postulate 9, a plane contains at least 3 non-collinear points. Let me fix that right here. And this is, again, I'm not going to go too deep in this one because you just kind of saw the explanation for it, just reversing it around if we were to start with the plane. Postulate 10, if 2 points lie on a plane, then the line containing them also lies in the plane. So if we were to have a plane and I were to give you 2 points, then this line that contains them, we can say with assumption, without proving anything, that line will also be in the plane as well. And then 11, if 2 planes intersect, their intersection is a line. So this is kind of hard to draw. I'm going to do my best here. So there's a plane going that direction. Let's say we got this one here. It's coming. You can kind of see where they're intersecting there. So I did my best with the drawing. We might have to get some real world. If you ever see me in person, I can kind of give you a real world example. But 2 planes will intersect at a line, just kind of like 2 lines will intersect at a point. So if we take these 2D figures, planes, they will intersect to form a one-dimensional figure, which is a line. So those are some examples of postulates. Now we're going to be looking at, okay, so we know some things. There's some things that we can assume to be true. How far can we go with this? So the directions here say when you interpret a diagram, you can only assume information about size or measure if it is marked. So there's a good idea there. Size and measure has to be marked. It's not I see it and I think that looks like a right angle, so I'm going to go ahead and assume it. We can't do that with size or measure. So here's some things, though, that we can assume based on this picture over to the right. All points that are on that plane, they are all coplanar. Since I just said it, all those points I see, D, C, E, B, F, A, G, they're all on plane P. So yes, I can assume they're coplanar. It says angle AHB, which is, let me get this one here, AHB, and angle, let's go ahead and write this in, angle AHF are a linear pair. And we see here, the reason why they're a linear pair is because they're making this straight line here, the sides of the angle, they're opposite rays, and they share a common vertex there, and they make a straight line. They make 180 degrees. So those are a linear pair. I'm going to use that new angle that I just talked about, which is angle AHF. It is vertical angles with angle, and we could name this one a couple different ways. But here's the 2 angles I'm going for here. I'm going to name that other angle BHD. You can name it a couple different things, but that's the one I'm going for. Those are vertical angles. They're directly across from each other. The sides are pairs of opposite rays. That's kind of what makes them vertical angles. AHJ and D. AHJ and D. So if we're going to look at those here, AH, J, and D, looks like they're all on the same line, so we can say that they are collinear. And then it says AD and BF intersects. Let me find them. AD and BF looks like they're intersecting here at point H. So all of these things are things that we can assume to be true, that we can read off the diagrams. I don't think there's too much of a surprise with this one. Here's what you cannot assume, which might be a little bit more important. You cannot assume that G, F, and E are collinear. If we take a look here, we cannot assume that there is one line that goes through all of these. This would be a bad thing. There's no line drawn, and we cannot assume that they do match up. Next one says BF and CE intersect. So again, BF right here and CE right here. There's no intersection shown. There's no parallel markings to be shown. So I can't assume without more information whether these are parallel, whether they're not parallel. I just can't do anything with it. Next one says the same 2 do not intersect. So I kind of covered both right there. I can't say whether they're parallel or not. BHA, let me see, BHA is this angle. And then CJA, which would be this angle. I cannot say these are congruent. So my markings here are bad. I don't know that they are congruent. There's no information about the size. Remember, we can not make assumptions about size or measure. And this next one here looks like there's a missing kind of marking here. BF perpendicular to CE, BF and CE, BF, CE, BF, CE. Yeah, that's confusing. Maybe I have the wrong thing down, but any of these. So let's just go to any of these. So this angle being 90 degrees or this angle being 90 degrees, that is what I would need there. I would actually need a marking of 90 degrees, which is a little box, because there's not, I cannot assume that as well. So make sure when it comes to parallel lines, when it comes to measurements, when it comes to lengths of segments, we need the actual information marked for us. And then one little example here, and then a definition, then an example, and we'll wrap up today's notes. It says a line is blank if and only if the line intersects the plane in a point and is perpendicular to every line in the plane that intersects at a point. Basically what we're saying here, a line is perpendicular to a plane if and only if it is perpendicular to every line in that plane. So if we were to have, this will be a fun little picture here for me to draw, this line coming through, intersecting here, and goes through. We can only say it's a right angle if it's perpendicular to all the lines that are crossing through this. So like I said, kind of a fun little picture to draw, just making sure that if a line is perpendicular to a plane, it's perpendicular to all those lines on that plane. And then last example here, which of the following statements cannot be assumed from the graph? So C, D, and E are collinear. No, we can say that because we can see C, oops, did not mean to screw that, C, D, and E, those are all good. They're all on the same line. They show that. Intersection of BD and EC is D. And no, we're able to see that right there. It is the intersection. BD and EC, here's that we cannot. So this one and this one. I'm gonna mark both of them. And the big thing here is this marking the perpendicular. In order to be perpendicular, we would need to have a right angle. So in both these situations, we would need to have a right angle marking where they say the intersection is. Obviously, I've drawn it in right now, but what they gave to us was things that could not be assumed. So these two right here cannot be assumed because we can not assume anything about size or measure when it comes to our geometric figures. So yeah, and I believe that is it. So that concludes the 2.4 notes. Make sure if you have any questions, please reach out, and I will talk to you guys later. Bye, guys.